All right, let's make some force diagrams. This one says that it's free particle model, worksheet 3, but this is the one that I have called number 4. This is force diagrams 4, because it's the fourth thing that I'm giving to you. Hope that wasn't confusing. Okay, so we need to make force diagrams. Determine the tension below, draw a force diagram for the system before solving the problem. So this is the thing I'm making a force diagram for, so make a dot for that. There's the force of gravity on this, I guess it's a ball from the entire Earth. And I know what that is because if I have the mass of something, I just multiply that by 10. And it's just hanging there, so not moving, so the forces must be balanced. So this is a force of tension on the ball from the cable, and that must also be 50 newtons. How about this one? This is suspended by 2 cables, and the force of gravity on the ball. Is this different? Are they just 50 newtons each? No. If there were 50 newtons of tension in each cable, then there would be a total of 100 up, and this would be accelerating upward. And that's not happening, so that means I'm going to make 2 little arrows that go up like that. And I don't know why I made that mark there, because that's not equal to anything. That's equal to 50. These ones, force of tension on the ball from this cable. So that's cable 1. And then here, force of tension on the ball from cable 2. Those are going to have to be equal to 25 each, because they're together they have to total 50. This is the secret. If you've ever seen or heard about the old carnival trick where the magician type person lies on a bed of nails, like really sharp nails, and doesn't get hurt. This is the secret to that, right? If you're lying on, if let's say you have a mass of 70 kilograms, so there would be, that means the gravitational force on you is 700 newtons. So whatever is holding you up, if you're not moving, then there's got to be 700 newtons of upward force on you. So if that is all coming from one sharp nail, 700 newtons from one sharp nail, that is going to pierce you. But if you have a board with a whole bunch of nails on it, then if you have, let's say, like 700 nails, then you could lie down on that and your weight would be supported by 700 of them. So that's only 1 Newton apiece, and 1 Newton is only like a quarter of a pound or so. So you can do it. You could be wondering, maybe, like, couldn't it be like 10 and 40? Like, how do we know that it's that they're equal? It's a little bit over our heads right now, but that has to do with rotation stuff. If one of them was more than the other, that would because they're not at the same spot, that would cause this to rotate, and it's not rotating. So anyway, in a situation like this, you're just going to assume that it's an even split, which is correct. All right, determine the tension in each cable below. These are 2 different things, so I need to make diagrams for each of them. I'll start with the 4 kilogram one. So here, force of gravity on the 4 kilogram one from the entire Earth, and it's not moving, so the force of tension on the 4 kilogram ball from the cable. And this is 40 newtons, 4 times 10, and so that must also be 40 newtons. Now this has 2 cables attached to it, and make no mistake, this cable is going to be pulling down on it, and this one is going to be pulling up on it. And gravity, just because there's 2 cables, it's not like gravity is going to back off. So you got gravity pulling down on the 7 kilogram ball from the entire Earth, and that's equal to 70 newtons. And then this cable pulling down on the 7 kilogram ball is the same as this cable, right? There's only one cable here, so there can't be different amounts of tension at the two ends of the cable. So it must be 40 newtons. Because it's the same cable. And if I've got 40 and 70, then the tension in this one, I guess we could call this cable 1, and this one is cable 2. This is on the 7 kilogram disc from cable 2. Then this has to be 110, because this has to balance those two. And that should make sense to us that this turned out to be 110, because this cable right here, this cable doesn't know that there's two different discs here, that one is 7 and one is 4 kilograms. Just like if you were holding this up, you wouldn't be able to tell the difference between if this is a 7 and a 4 or if it's just like one 11 kilogram disc. So it makes sense that this tension up here is going to have to be supporting the whole thing. All right. Here, find the horizontal and vertical components of the tension in the fishing line. So I'm going to make a force diagram of the rod from the top of the rod here. Now, there's a tension force pulling this way, right? And all we're doing here is just breaking this up into its components. So I'm going to make the X component and the Y component like this. This is 38 newtons, right? And what's this angle? Is it 55? Is it the same as this, or is it 35, or what? Well, some little things from geometry we have to remember now and again. This angle and this angle are equal to each other. The nice thing for us about angles is if you draw your angles, you got to avoid the temptation to make everything look like a 45-degree angle, because then you can't tell which angle is bigger or smaller in a triangle because they're both 45. If you make your diagram like as faithful as you can to what's actually happening, then in right triangles, big angles are equal to big angles and little angles are equal to little angles. So this is the 55 anyway. So this right here would be 38 times the cosine of 55, because it's adjacent to this, and this is 38 sine 55. And you can do that. I'll just pop out the numbers real quick from my calculator and check my mode, because if you're in a calculus class especially, you got to watch out. Make sure you're in degree mode. So I got 38 cosine 55 is about 21.8 newtons, and 38 times the sine of 55 is 31.1. That's all we were being asked to do there. All right, how about this problem? A suspension bridge cable is connected to its anchor at a 20-degree angle. Draw a force diagram for the anchor, and then find the vertical and the horizontal component forces on the anchor by the cable. This one's a little tricky to do, to figure out exactly like what the forces are. So I'll show you how I'm going to do it. The main thing, if you took this and broke it up into with a 20-degree angle, that's the main thing I'm interested in here. So I'm going to draw my axes. I'm not on a hill, so these are just regular axes. And this force is going like this, and it's 15,000 newtons, and this is 20 degrees. So let's break this up first. So 15,000 times the cosine of 20 is going to be this. That's 14,095 You know, I'm going to call that's too many sig figs. So that's 4 sig figs right there. That's about the most that I have a tolerance for. Sorry, that's one's in the wrong place. Here's 3 sig figs if I round to the nearest 100 there. So if you're thinking, oh, well, if that's 14,100 of it, then there's 900 of it left for here. No, that's not how vectors work. It's 2 sides of a triangle. So to find the other one, I got 15,000 times the sine of 20. That's how we find it. And it's about 5,130. That's also 3 sig figs there. Good. Now, this thing, it's anchored here. It's definitely not moving. So that means there must be something here, force of gravity on the anchor from the Earth, that's equal to that. And then there must be something here. Those would be equal, and then these would be equal. There must be something here. And this is the one that I think is kind of tricky to just, like, what is it? I guess it's some kind of friction or something. I mean, it's whatever's holding this in place. It's kind of like cemented into the ground, so I don't know. It doesn't really seem quite like friction to me, but I'm going to call it that anyway. I don't care what you called this. Just want to have the diagram right. Anchor from the ground, I suppose. And that's got to be equal to 14,100. So this is the part that I'm most interested in this problem. And then recognizing that if it is in fact not moving, then got to be balancing forces. All right. So how about this? Rock sits on a hill. The hill is like this. This is a 75 degree. This is the big angle, so the actual slope of the hill is 15 degrees. Now I'm going to try to make my axes here as faithful as I can to that. So I was trying to make this, as I was drawing this, trying to make it parallel to that. And then go ahead and tilt your paper so that that's horizontal, so you can make your other axis nice and perpendicular like. Okay, so there's my axes. I'm going to tilt back because gravity doesn't care if you're on a hill or whatever. So do that. That is my force of gravity on that. What is this thing? A rock. On a rock from the entire Earth. And do we know? Oh, 25 newtons, it says here. So I don't need to multiply this by 10. It's already in newtons. So what does that mean the mass of the rock is? So that means the rock must have a mass of 2.5 kilograms, right? Because it already got multiplied by 10. Want to get back to the mass? Divide by 10. Okay, so now I'm going to tilt like this. So this force of gravity, I need to break it up into the components here. This and this. And I've got that 75 degree angle here. This is 15, this is 15. So if this is 25, then you could either, if you want to use this 15 degree angle, then this is opposite to that. So you could do 25 times the sine of 15 degrees, because it's opposite to that 15 degree angle. And watch what that's equal to. 25 sine 15. That's equal to about 6.5. Or you're like, oh, well, I was thinking about that 75 degree angle and it's adjacent to that. So would that have got me the wrong answer? Is it the wrong way to do it? No, that works too. 25 times the cosine of 75, because that's adjacent to that. 25 cosine 75, guess what that's equal to? Oh, snap. Now this one, same thing. You could either do 25 times the sine of this right here. If you're doing sine is opposite, so that'd be sine of 75. 24.1. Or if you're looking at the 15 degree angle and you're like, oh, that's adjacent to that. Sure, you're right, it is. That's 25 cosine 15. also 24.1. So it doesn't matter, you just have to pay attention to which angle you're using and use your trig knowledge. Now, if that's true, once we got that broken up, this thing's not moving, so that means there must be something to balance this. What would that be? Well, that's the force of friction, right? Stopping the rock from sliding down the hill. Force of friction on the rock from the hillside, or the ground, you could say, whatever. And then it's not moving up and down, so there must be a force here that's equal to that. What's that? That's a normal force. That's that support force. Remember that normal means perpendicular. It's perpendicular to the hill. It's not possible for a hill that's slanted like this to support something straight up. That is not possible. So this is a support force, and it must be equal to 24.1. Oh, I forgot the other parts of that. Support force on the rock from the hill. 24.1. All right. So let's just read through this, make sure we answer the questions as we were supposed to. This says, draw a force diagram for the rock that allows you to determine how much of the rock's weight is parallel to the hill. So that's this, right, in the direction of the hill. And how much of the rock's weight is perpendicular to the hill. Perpendicular to the hill. That's this. So yeah, we did that in the context of doing the force diagram. But that's what I want you to be able to do, make a diagram like that. And I'm going to stop here, put the last three in a separate video.